So that's basically the the motivation. So let's look at the simple overview of the multimodality very quickly. So we started to look into multimodality actually, right, I think from week 6 or even before, yeah. So week 5, week 6, something like that. So when we look at this paper, attention all you need. So what we had is we had English language going here, and we have, for example, French language going here at the input, yeah. So you see that these you can consider. So what we had was English language was interacting here with transformer blocks, and then you are doing cross attention using K and V coming from here, and Q was coming from the French. So and we saw that when we are here at this stage before the skip connection, the French which is in Q tokens are being so you model the similarity of French to English in terms of K and V, and then you encode it in terms of English, and by the time you are at this stage, so these French tokens are now represented in terms of English token, yeah. And then we had the skip connection. So due to skip connection, basically what we had at this stage is that half of it is a combination of basically French and English both, yeah. So you can see that this was already multimodal, so it has both French and English, yeah. The tokens will have started to have both. So if you consider that instead of English and French, if you pass here the visual input, so if it is vision, and if this part is text or any other modality, then you will start to go from vision to text, yeah. So that architecture which we covered in a lot of details was already multimodal, yeah. So that was very simple way of doing multimodality. So we will look into quite advanced way of doing multimodality. Still simple, but more latest, let's say. So this is a nice overview paper. So this is also coming from one of the colleague at CVSSP. So, and this is very easily illustrated. You can see that the tokens are represented from two different modalities, and green tokens represent one modality and the purple token represent the other modality. So what you can do in the simplest setting is that you can take, so there are multiple ways, and they are not covering all the possible ways. They are covering just 6 of the possible ways. So what you can do is that you have tokens from modality A. So these green tokens are from modality A, and these purple token are from modality B, and you can just take the sum of that at the input. So you do the tokenization and you take the sum and you pass it to the transformer block. And this transformer block, this transformer layer is actually transformer blocks. You have multiple of them, and this TL will be multimodal as in this case. So, and then there is another possibility. Instead of summing them, you pass modality A and modality B as concatenated together, yeah. So if you have 100 token from modality 1, 100 token from modality 2, you will end up with 200 tokens, yeah. And then you will pass it through the transformer block, and the transformer block will be multimodal in this case. So there are advantages and disadvantages of these approaches. For example, if you are going with first one, and we know that attention operation has complexity and square complexity. So in this case, NA and NB is the same. So in the first scenario, the complexity will be NA square, yeah. In the second one, the complexity will be higher, so it will be ONA plus NB square, yeah. So the complexity in this scenario, in the second case, is higher. But there are different advantages. Second approach may work slightly better. Okay. So then you can choose to have modality specific encoders. So this is modality specific encoder for modality 1 and modality 2. So you pass the token of first modality to first transformer, second modality to second transformer, and then you can do the concatenation of that and have the multimodal transformer at the end. Yeah. So this is another flavor. You may want to have the common transformer first, the common shared modality transformer blocks first. So you concatenate the tokens from modality A and modality B, you pass it through a transformer layer, and then you may want to have modality specific information at the end. So I will cover that some of the scenario where these things will be applicable and where these things will be useful. So for example, here in this scenario, you may wonder why it will be meaningful to do the sharing of the modality first and then independent modality separately. So for the case of, for example, if you want to combine the modality of infrared and visible. So there are a lot of, both are kind of imaging modality. So one is visible, one is infrared or thermal. And there is a lot of things which could be shared and which would be common because modality being imaging modalities, both of them. So you may want to extract the feature which are quite generic early on, and then you have some specific characteristics which are related to visible images and with specific characteristics which are related to infrared, and you want to do that processing separately later. So in that scenario, you may want to go to option D. Yeah? So you may want to choose option D. For the case of, I don't know, RGB and depth or infrared, yeah, images. So that's one of the example. So in why would you like C? So for example, you may have vision and text. Now vision and text are quite different modalities in nature, yeah. So they do represent probably the same underlying concepts, but the modality by itself is quite different. So you may want to have modality specific operation first to model vision and model language, and then you may want to combine the shared knowledge at the end because both of them are reflecting the same thing, yeah. So in that case, you would have, so for example, for vision language scenarios, vision audio scenario, you may want to do this kind of processing. And we will look into examples of all of these scenarios later. So there is other way to do the fusion of the modalities as well. So we have seen it. We have seen in the cross attention, for example, when we were looking at attention all you need paper. So you can take the query from one modality, and key and values are coming from the other modality. So it's a cross attention, yeah, and vice versa. So you can do cross attention both ways. And that way, you will share the information of one modality via K and V of the other modality and vice versa. You can choose to do this cross attention early on, and then you can concatenate the modality and do the operation later on. So based on these, different schemes have different advantages and different strength, and based on the application area, you will choose one or the other, and based on the requirement you have. And based on the complexity you are going to have. So in this lecture, we will go into a little bit of mathematics as well. So let's look into some of the mathematics which is going on behind this. Yeah. So this is a table which is representing essentially what we are looking at here. Yeah. So let's look at the example of case A. So I have modality token from A modality and modality B. So what I am doing simply in this scenario is that I am taking the tokens from modality A, it's represented by ZA and ZB, and I am multiplying the token of modality A with alpha, to multiplying the token of modality B with beta, and I am basically taking a linear combination of them. Yeah, so we have seen that. So token-wise summation. Okay, so for the second scenario, what I am doing is I am just concatenating the two tokens. So this token from modality A, modality B. So you can say that this is ZB, ZA, and I am just doing the concatenation, and that is reflected here in terms of concatenation operation. So this C represent concatenation. TF means transformer blocks. Yeah. So that could be one layer or that could be 10 layers. Yeah. But these are standard transformer block layers where you have attention layers, attention block, and then you have feed-forward block as the second processing. Okay. So that is another. So basically, all of these mathematical equations, which we have already discussed that the number of tokens in the modality A is NA, so you have NA squared, and in the other case you have NA plus NB squared, so the complexity will be higher. So if you look at the paper, there are citations corresponding to every scenario which we are having, and those paper, you can go and look into those papers further, and you will see that what kind of application areas these multimodalities are covered. Okay, so in the case of third scenario, what we did is that we have a little transformer block for modality A, and we have a little transformer block for modality B, and then we did the concatenation and we pass it to the transformer, and that is written exactly in one line of math. So you pass the modality A through transformer 1, you pass the modality B through transformer 2, So modality A from transformer for transformer 1, modality B from transformer 2, and then you concatenate it and pass it through third transformer block. Yeah, so it's very, very straightforward. And same is true if you go to fourth modality. You share the modality first, and then you have the separate. So you do the concatenation first in that scenario of modalities, and then so this is token from modality A, modality B, you concatenate, you shared it, then you split those tokens to A and B, and then you pass through individual separate transformer, and so on and so forth. The next one was cross attention, so you have query from one modality, K and B from the other modality, you pass it through multi-head self-attention, and you do the same with the other modality, query from modality A, K and B from modality B, and then basically you pass it through multi-head self-attention, and that was your other processing. So the last one, you do this in the last one you do the cross attention first and then you combine it. Yeah, so that is depicted here, cross attention, and then you have shared transformer block. So that is the overview of different possibilities which are there. This does not cover all of the possibility. We will look into more of the possibilities later, but these cover very basic set of possibilities. Yeah, so when it comes to processing of the modality, even if you are processing of the modality separately, which is predominantly the design nowadays, so there are choices that how much compute you want to spend on one modality and how much compute you want to spend on the other modality. And those choices are determined by the complexity of the modality and application area. Yeah? So these are some of the flavors. So again, the example which I am going to use is vision and text. Yeah? So there is visual encoder and text encoder. And image and vision or video is quite complex usually, so you may choose to have a long encoder for the modality for vision, and you may have just text embedding, tokenization for text. Yeah, and then you have shallow modality interaction, so you can have that. So that's one way to do it. Another way to do it is that you give quite deep architectures for vision encoder and quite deep architecture for visual encoder, so quite a lot of layers, maybe 12 layers each, and then you have a shallow modality encoder as well. Yeah, so multimodal information is done by shallow interaction. So method like CLIP, which we will study today, fall into this category. Okay, so you may choose to have shallow text encoder and deep, for example, visual encoder, and then you have deep multimodal interaction as well. So methods which are coming particularly from LLM-based interaction or vision and LLM-based interaction and so on and so forth, they fall into this category. You may choose to have a shallow textual encoder, and you may choose to have a shallow visual encoder, and you may want to have multimodality, which is quite deep, and methods like SimVLM from Google, and one of the methods which is built in parallel, CLMIU from our group, they fall under this category. And they enable different kinds of application, and we will look into those application